Is he your TA? What's with that? All this is too flat of a hierarchy. It's the Berkeley way. 9, 8, 7, 6, 5, 4, 3, 2, 1. Welcome to EE123, Lecture 7. Woo! It's a deeper voice there. So you're dropping like flies, huh? Or just be polite? You what? Not yet. Oh, it's online? Oh, that's true. But all the cool stuff is not there. Okay. So today's my favorite lecture in the whole class. Well, I changed my mind. Not this week. I mean, after going through these slides, I realized actually that this is my favorite lecture. So the FFT. There's something really exciting about FFT is, it kind of revolutionized the way people think about computation, about algorithms. Instead of thinking from just a simple theoretical point of view, when you go and implement things, there are ways to implement things fast. And that made a huge change in how we do scientific computing, or anything computational in general. So exploiting structure within a problem. One of the structures that people use all the time today is sparse matrices. If you can represent something as sparse matrices, you can compute these operations very fast. Another class is those matrices or systems that have a lot of structures in them. And we'll see a few of them during the class. One of them is the FFT. We're going to talk about the wavelet transform, and we're also going to talk about multi-rate signal processing, which exploits, again, redundancy in computation when we do upsampling and downsampling operation as well as filtering. Okay, so we'll get to this. Now, just before we start, anybody knows what is this? You seen this before? A Raspberry Pi. Who has a Raspberry Pi at home? Oh, it's quite a few of you, right? It's a small computer. So it's a small computer. It can run Linux. I think it can also run Windows. Can it run Windows? It's an ARM processor. It has HDMI output. It's actually quite powerful for something so small. Costs about $35. Has 4 cores. This version, and it's used for anything that you want to do with kind of embedded stuff. It runs out of 5 volts source. It can run out of battery. Now you can buy the Raspberry Pi Zero, it's called, and it's a $5 small computer. So quite powerful. Okay. So this is kind of the stuff that people that like to make stuff would use. And one of the things that they use is those GPIO ports. GPIO, general purpose I/O ports, that you can control to switch on lights and so on and so forth. So there's 2 ports that are actually interesting here that I want to point out. One of them is port 4, and the other one is port 18. As it turns out, these are connected to a programmable PLL. Who does not know what a PLL means? Okay. A PLL is what's called a phased lock loop. Basically, generating a frequency. You use that to generate clocks, to control for example, another board. You can use it to generate other frequencies and so on and so forth. And a programmable PLL just allows you to set the frequency that you want through software. Okay. Now these ports here actually produce a square wave that I think goes from DC. I'm not sure if it really goes all the way to DC. It's pretty close to DC, all the way to 200 megahertz. Okay, so it's quite substantial range of frequencies that you can generate using this PLL. And the idea behind this programmable PLL was to, if you want to control another board from the GPIO and be able to synchronize, clocks and things like that. Now, the thing is, people are really creative, and this is what I like about humanity. There's a lot of creativity out there. So, if you can generate a frequency that's programmable, somebody's going to make a radio out of it. Okay? Any frequency that you can program, somebody is going to make a radio out of it. And there's a few projects that span out of the the people have figured out that you can use this for this. So the first one was from I think King's College, if I'm not mistaken, in the UK, where they turned the Raspberry Pi into an FM transmitter. They use the direct memory access to speed things up, but basically you feed the PLL with the right frequencies to frequency modulate it and create a FM radio. Here's an example. I just showed you the video. It's just so cool. Somebody made a video based on these. It's a 2-minute video.
So this may not seem that cool. It's just a hand transceiver tuned to 100 megahertz FM playing the William Tell Overture. It's not that cool, except for the fact that it's being broadcasted by the Raspberry Pi. This was a tutorial I saw posted to Reddit this morning, and I had to try it out immediately. It's by the Imperial College Robotics Society. They show you how to use the Raspberry Pi as a personal low-power FM transmitter. The best part about this project, or the two best parts about this project, one is that it's so easy to get running. You just use their code, you run it in Python, you give it a WAV file, and it just broadcasts it. The second best thing about this project is you don't need much hardware. This is all you need. This is just a piece of wire. I cut it to 20 centimeters, plugged it to pin 40, and I've got a personal FM transmitter. So I thought this was so cool, I had to post a video about it and show it working, and I'll post a link in the description of this video to the tutorial. Check that out, and if you do something with it, let me know.
That's pretty awesome, right? So anybody that has one of these can just go home today and just do it. It's really easy to do. And basically use this as, at least to create some frequency modulated signals. Then, people thought about it a little bit more, realized that pin 18, you can also change the amplitude by about 8 levels. So, hey, maybe you can do AM modulation, maybe even single sideband and so on and so forth. This is the project RPI-TX. And then there's another interesting one. It's called Whispery Pi. I'll show you what does it mean. But and then QRPI. This project over here allows you to do a full transmit receive using the USB dongles that you're going to get as a receiver and the Raspberry Pi as a transmitter. So all in a single embedded computer, which is, I think, pretty awesome. Now, you'd say, well, you transmit a square wave. What is the effect of actually using a square wave as opposed to pure frequency? What do you think? Oh, harmonics. And why would you have harmonics?
Because there's higher frequency components basically to make the sine wave into the square wave.
Okay, so you can take a square wave as something periodic. You can compute a Fourier series of a periodic signal. If you compute a Fourier series, you realize that, hey, it's just a sum of sinusoids at odd harmonics with some coefficients to them. Okay, so there's going to be some harmonics generated, and those harmonics, of course, decay with a rate of 1 over the odd harmonics. Okay, so there's a lot of very strong odd harmonics. So that would be illegal and problematic to transmit with this device by creating so much spectrum. I mean, it's not a big deal if you just do it at home. It's really low power, so it is within the legal limits. But you have to be careful if you want to amplify it. So here's another project that from someone from Hungary. It's called QRPI, where they created a small daughter board which has a analog bandpass filter and some gain that's tuned around 14 megahertz. Turns out to be an amateur radio band on a 20-meter band, 14 megahertz. And the gain allows you to put about 0.1 watts out of it. So you ask, well, what can you do with 0.1 watts? Well, there's a lot of things that people have developed, and one of the cool things that if you come to my lectures and look a little bit about what amateur radio is, people develop these weak signal communication modes where they transmit for a long time at a really low bit rate, very low power, still be able to communicate over really large distances. So I got excited. This guy actually sent, his name is Zoltan, he sent me a sample, so I just hooked it to my Raspberry Pi, installed this, connected it to an antenna for 20 meter outside my house, and run this Whisper type of protocol where a lot of people in the world are running receivers for it. So they pick it up, and if they actually pick up your signal, they'll upload it to a website that you can track, what's the propagation. So guess what? This is from last night. This is the last 24 hours. All the stations that were able to pick up my 0.1 watt signal as my beacon is transmitting. I think it's extraordinary what you can do with, just a little bit of signal processing, some hardware hacking, and putting all these pieces of software together. Any questions about that? Questions? Yep. Oh, there is actually VE7 KP8. It depends how many people are running it. The other thing is my antenna is pointing north, and so it's radiating east-west mostly. So there is some energy going a little bit north that way and that way, but not that way. Yeah. 2 weeks ago, I actually got picked up in Australia too. So if you do miles divided by watts, that's a lot. I think it's 100,000. Okay, so there's pretty cool stuff that everyone can basically experiment with. So I think it's pretty amazing. All right. So what did we talk about last time? Last time we talked about discrete Fourier transform. That was my previous favorite lecture. We talked about linear convolution through a circular one, and then using linear convolution using the DFT. We talked about two methods: overlap add, overlap save. And today we're going to talk about the fast Fourier transform. Before this, lab 1 is out, and it's due next Thursday. I will talk about the lab on Friday, and I will not record this for you guys listening. Okay. Ham lecture tonight, 6:30 to 8:30 p.m. Okay, so don't mess it up. We mentioned circular convolution. Emails. We mentioned circular convolutions last time, and if you think about what is a circular convolution, it's a mathematical operation, it's linear, hence can be described over finite sequences, hence can be described by simple matrix operation, linear algebra, the cool things that you like doing. Who likes linear algebra here? Absolutely. When I learned linear algebra, I did not know, it sounded cool, but I did not know what it's all about. And I have to say, I use it every day for the last 20 years. Wow, it's been that long. Okay, so if you think about the operation of performing circular convolution, you can take the coefficients of the filter that you want to circularly convolve with, and put them in a matrix in a particular way that will be equivalent to performing that circular convolution. And as it turns out, circular convolution is a circulant matrix. Kind of makes sense because you have your filter and you multiply and add. What's multiply and add is an inner product between a vector and another vector. Okay, that's multiply add. Okay? And if I want to compute that circular convolution at a particular point, I need to place that filter at a particular offset such that they fit. And then if I want to move it by one sample, I'm just going to, the next row will be just shifted by one sample, circularly, and so on and so forth. So this is effectively what you're getting here. Okay? Circular convolution will exactly correspond to putting your filter on as a vector and then circularly shifting it. Hence, circulant matrices. Okay? So that operation could be described by a circulant matrix, which is great. But here's what's exciting about circulant matrices. Circulant matrices have a particular structure. It's circulant. And as it turns out, the DFT matrix, its rows and actually columns, are eigenvectors of circulant matrices. Isn't that crazy? It's crazy. Are eigenvalues. How can you show? You're going to see in your homework. Yeah. Eigenvectors. Where do you say? The eigen. Oh boy. Eigenvectors, circular. Eigenvectors are DFT. No, eigenvectors are DFT coefficients. The eigenvalues are the DFT of the filter. Yeah. No. Eigenvectors are DFT coefficients. So the coefficients of the DFT operations. Well, I guess I don't know. Yeah, maybe you're right. Okay. You get your $2. Oh boy. Eigenvalues are the DTFT coefficient, and remind me, where's the account? Last name? Last name? $2. I'm at a 1, 2, 3, 4, 5, 6, 7, $14 loss. It's pretty good. What? Yeah, but like I pay myself, so it doesn't, I'm still at a loss. Okay. So, I mean, this is pretty interesting if you think about this. Okay, this is pretty interesting. Okay, so you're going to see this in the homework. But no matter what circular matrix is, the eigenvectors are going to be the DFT coefficients. The DFT, the basis. Okay, basis functions, effectively. Okay, so those are going to be the eigenvectors. I mean, it kind of makes sense because whenever you have such structure, it's always a filter. Right? It's always a circular filtering operation. It's always circular convolution. It's just the different coefficients of that operation. So again, performing a DFT kind of diagonalizes it. So if we have the DFT, I mean, if we can take the circular matrix and then diagonalize it using those eigenvalues by multiplying with the eigenvectors from left side and the inverse from the right-hand side, then you'll see that the diagonal are the DFT coefficients, which are also the eigenvalues. Okay, so that's pretty cool. If you want to compute, a DFT of something, you could potentially do more computation by putting that in a circular matrix and computing the eigenvalue decomposition. Okay, if you really wanted to, but of course it doesn't make sense. Okay. So then let's look a little bit. Let's multiply by W sub n, so by the DFT matrix from the right-hand side. So if we multiply by the right-hand side, this goes away and we don't have it, and then we have here, okay, the W sub n. And then multiply both sides by x, so we multiply here by x and we multiply here by x. And here what it really means. It means that if I take a signal and I compute its DFT, the operation of filtering, or the circular convolution, is really multiplying by the DFT of the filter. That is equivalent to performing the circular convolution and then taking the DFT. Okay, so circular convolution in one domain is equivalent to a multiplication in the other domain. This is basically a proof if you can show that that the DFT is in fact diagonalizing circular matrices. Okay, and we will show that in the homework. Okay, so any questions about that? Yep. It's the DFT matrix. It's a matrix that evaluates an n-point DFT. Okay, so it's all the the basis functions of the DFT. We show that we can represent a DFT operation through a matrix multiplication. Does it make sense? Yeah, it's all the complex exponentials and the right. Yeah, and of course it has structure. Yeah. The what? That's so. Man, I should just skip slides, right? Quickly. Thank you all. That's amazing. Wow, I'm impressed. You guys rock. You guys pay attention. This motivation of money really works. Angela, 4. You're doing well. Okay. I'll post the scores every week. Okay. So now we want to compute. Okay, so it's great. We can do circular convolution simply using the DFT. But we don't know how to compute it fast. We want to compute it fast. An efficient method. These are the operations. Okay. These are the operations where W sub n to the power of kn look like that. Sorry, W sub n look like that. Okay? We want to exploit structure in that matrix in order to be able to compute both forward and inverse DFT. Now recall, what if we know how to compute the forward DFT fast? Does it help us to compute the inverse? Yes, because we showed last time that if we want to compute the inverse, we need to take our sequence, compute its conjugate, compute the forward FFT, compute its conjugate, and divide by n. That will give you exactly the same thing. Okay, so we just need one procedure in order to do this. Okay, one function. Forward, it will also implement then the inverse. Again, straightforward computation of an n-point DFT that doesn't exploit the structure requires n squared. But we would like to use calculations that we've already done, maybe to do overall less. Okay? I mean, that's the whole idea. You don't want to waste computation. You don't want to multiply, for example, by zeros. Right? That's a waste. You don't want to, if you computed something, why compute it again? Maybe we can just store it or do something with it. Okay? And if you think of fast Fourier transform algorithms, they enable the computation with an n log n, and that n log n will come by when we look at the structure. Why is it actually log n? Okay? But the log n is much less than n, especially when it grows. Okay? So log is like this. Like, what's a constant? From an engineering point of view. Log of n. Log of n is 6. For all purposes, I mean, it's approximately 6. Whatever number it is, log of n is 6. Right? From an engineering point of view. Right? Okay? So log of n, it's not 6. It grows a little bit more, but not as fast as n. By the way, this is copyrighted to Stephen Boyd. The log of n equals 6. So I'm just reiterating that. I thought it was funny when I took that class. I guess you kind of find it funny as well. Okay, so let's see how things grow. If you look at n, 16, 128, and so on and so forth, n squared grows significantly faster. N log n doesn't grow as fast. And if you just look at what's the ratio between n squared and n log n, when we talk about like 6 megapixels, 6 mega samples, it's a factor of 10 to the fifth, So it's like a huge factor as you increase. Okay, so it's a good motivation to do n log n as opposed to n squared. All right. So if you think of the operation that we're going to do, if you look at that matrix, the DFT matrix, this has this exponent, it's different exponents of this omega sub n. And so maybe we can exploit that kind of structure in that, not omega, w sub n, in this w sub n, exploit the structure in order to do fast computation. So we're going to exploit the following properties of w sub n to the power of kn. First of all, conjugate symmetry. If you take n minus n, then this is equivalent to w sub n to the power of kn conjugate. Okay? So it's a circularly symmetricity about it. Okay? So this is one property. So if you, first of all, okay, so the way you get this is that it is periodic with n, and so k to the power of n minus n will be w sub n minus kn, and that's equivalent, of course, to the conjugate of that. The other one is the periodicity in n and k, and we showed that, right? It's kind of like a clock, remember? Right? W sub n, when we look at the phase, phase repeats, and it repeats every n. So if you just switch the n's or the k's, you get some periodicity. And so if you add a capital N to a small n, it's the same as adding a capital N to a k, and it's equivalent to not adding them at all. Yes? The what? No, it's just for the basis ones. It's not. There's no signal. Okay. And then the other one, which is really useful, if you take a power of that, it's equivalent to computing w sub n over 2. Okay, it's exactly the same if you just want to write it. Okay, it kind of makes sense because you go faster. If you go faster, it's like not having everything. It's like just going on a smaller clock. So the way that people do, there's a lot of FFT type algorithms out there. But most of them decompose a computation into successively smaller DFTs. So you have a big DFT you want to compute, you do a few smaller DFTs. And then you have these few smaller DFTs that you need to compute, then you do few smaller DFTs. And then you have those, then you do few smaller DFTs as well. And as it turns out, as you decompose into smaller and smaller, it's kind of like where the log comes in. When you break something to half and half and half, that's where the log comes in. Okay, so you'll see that. Okay. There's two algorithms that we're going to kind of visit. One of them is called decimation in time, so you break your sequence in time. The other one is you break your sequence in the frequency. Okay, and then from that, you try to do these smaller DFTs. Okay, we're going to mostly discuss the decimation in time and have one in the exam that talks about this. No, I don't know, maybe decimation and frequency. We're going to mention decimation and frequency, but it's same, but different. It's the same type of approach. Now, just for ease, we're going to assume that x of n is a sequence of power of 2. It doesn't have to be a power of 2. There are the fast Fourier transform algorithms that don't need to have a power of 2. But right now, just for ease, we're going to assume a power of 2. And if it's not a power of 2, we're going to zero pad to the closest power of 2 to compute a DFT. Okay? So we're just going to assume a slightly longer sequence. Okay? Yes? Well, it's just going to... So if you add zeros, right, we show that it's just sampling the DTFT more finely. Right? So in terms of getting the spectrum of information is the same. Right? It's just sampling the DTFT more finely. You don't get more information, it's just sample it better. That's pretty much. Right? By closest, I don't mean going backwards. Okay, not throwing away samples, but just adding zeros to the next par of 2. And you don't have to do this, but just for simplicity, we're going to assume it right now. Okay. So, are you ready? Because this is going to be cool. Okay. And it's all about looking at a problem and exploiting structure. Now, the thing is, once people realize, DFT exists, they realize, hey, there's other operations that you can think of that have this kind of a structure. And then a whole class of these fast algorithms evolved, okay, by looking at different symmetries and properties of how matrices and systems are constructed such that you can do this. Or can be approximated. Okay, there's a lot of approximation algorithms that people use to approximate something that is close to a particular structure you can compute fast. Okay, so you trade off accuracy with speed. Okay, that's another thing that a lot people do. So it's more general than just the FFT, but the FFT is classic. It's like seeing Gone with the Wind. You got to watch that, right? Who watched Gone with the Wind? Well, everybody knows, everybody knows like quotes from Gone with the Wind, right? Like, frankly, my dear, I don't give a. Right? Everybody knows that, right? So obviously you need to do this, to go through the FFT. You got the point. Okay. So in order to speed the DFT, we have to start with it. So let's just write it down, okay? This is the DFT. Stare at this for a second, okay? We sum from n equals 0, n minus 1, over all the n's, and then we have this kn here. We're going to do what's called decimation in time. Hey, look. The evens and odds don't feel right to put them together. Because odd numbers don't divide by 2. Even numbers do divide by 2. So let's separate them into groups. Okay? It's kind of like a divide and conquer kind of thing. It's actually a divide and conquer type problem. In fact, it's a classic divide and conquer type of thing. Yeah. So let's divide. But I don't like the conquer thing. It's like militant. So let's divide and gain. Look, something positive about it. Okay. So x of k, we sum over the even ones and we sum over the odd ones, and then we add them together. So who cares? Why would you even care? Well, each of these two are kind of look like DFTs, almost, but each of them with half the samples. It's almost, they don't look exactly like DFTs, but like almost like DFTs. So let's try to make them look like DFTs. Because if we can make them look like DFTs, then that's kind of our aim, right? So, n is a problem if we want to sum over the evens and over the odds. So let's just change variables and call n to be 2r. Okay. And then for the even ones, and then n equal 2r plus 1 for the odd ones. Okay. So now my sum, I can sum over r instead of summing over n's, and I can sum normally, like 1, 2, 3, as opposed to 1, 3, 4, 1, 3, 5, stuff like that. So I sum this, so I get x of 2r w sub n to the power of 2rk. And here I get the sum over r's as well, of x of 2r plus 1, and then w sub n 2r plus 1 times k. Okay, so I just replaced that. By the way, the slides are always available, hopefully before midnight, the night before, if I remember to post. Did I post them? I did, right? Sometimes I do forget to do this make update. We actually sent it. But if you don't see them, you can actually send a message, and I'll do that in the first thing in the morning. You can print them. Okay, so I did that. That's great. But remember, there were some properties of this W sub n to the power of r, right, that we can exploit. So let's think about this. What is W sub n to the power of 2rk? Well, the 2 can just go down. Okay, it's like same thing. You just like knock it down, it goes down. Didn't change. Okay? The way to show it is that if you write it that way, you just reorder things differently, and then you get that result. Okay, so it's pretty easy to show. Okay? So remember this trick. This is a cool trick. This, by the way, notation is really important. Notation is super important for development of mathematics and the development of, mathematical thinking. Think about if you had to use Roman numbers to do these type of calculations. I mean, you could, but it would be quite hard. Hence, notation makes it really important in order to be able to solve things. Okay? When you write your papers, think about that. Okay, what type of notation you use, that's going to change everything from understanding your paper as well as deriving things. Okay, so notation is often a key. Okay. All right, so let's write it down. Okay, so we have this with n now equal to. This is what is this sequence really? If you think about it, that sequence is what size? It's the size n over 2, right? Because we jump every 2. It goes from r equals 0 all the way to n over 2. That's great. Well, that looks to me, at least, it looks like a DFT of size n over 2. What about the other guy? Well, the other guy also looks like a DFT, and the difference that I jumped one slide back. When we went from here to here, I took this 1 and I moved it outside of the sum. 1 times k, w sub n to the power of k. I moved it outside of the sum because it doesn't have an r in it. Okay. So this is what it is. So this again also looks like a DFT, except it has some factor that does depend on a particular k that's outside. Okay. So I'm going to write it as g of k, which is the DFT of the even numbers, and h of k is the DFT of the odd indices in our sequence. Okay. And the odd ones are multiplied by some what's called a twiddle factor. But if essentially it is a linear phase with k. Okay, you see there's a linear phase here. Because what's w sub n? It's phase that changes linearly as a function of k. Right, it's a linear phase. What does the linear phase does if you multiply a linear phase with a DFT? What's multiply with a linear phase in the frequency domain? What does it do? It's a shift in the time domain, right? Well, it kind of makes sense. These are odd samples. They're shifted by 1 from, right? And if we just compute the DFT on them, it's not going to put them in the right place. We need to multiply by some linear phase in order to put them in the right place. Yeah? Makes sense? It's another way to think about this. Okay, so now we define these to be the DFT of the even. This is the DFT of the odds. Fantastic. And then in order to get back the original sequence, I need to kind of multiply by a linear phase one of them. Okay. So let's write it down. Okay? I'm going to split into the evens. I'm going to split into the odd. I'm going to compute an n-point DFT. I'm going to get a result. I'm going to take this, n over 2-point DFT, going to get a result. And then I'm going to take the result from here, multiply by omega w sub n to the power of k, which here k is 0, but basically 1. and then add it to this result. To get x1, I'm going to take g1 and then take h1, multiply h1 by w sub n to the power of 1, and then get x1. Okay, so that's where the k shows in, and so on and so forth. Does this make sense? Okay. If you count the number of calculations, nothing has changed. Okay? It's exactly the same number of calculations. Like an order of calculations. We haven't changed anything there. We'll get to that. Because this is still, we need to compute like n over 2 square. And this is n over 2 square. Right? Still same number of order of operations. Okay? So you cannot stop here. In order to get this log, you have to go down. We'll see that. Okay. But is this all the structure that there is? Not really all the structure. There's more structure to be exploited. So let's look at these guys, okay, and see what's going on there. Okay. Yeah. Let's look at these guys. So both G and K and H of K are periodic with a period of n over 2, okay? Right? Because they're n over 2 DFT sequences. Right? So if I add that, you can see that it's exactly the same. But it kind of makes sense because these are n over 2 DFT sequences. DFT sequences are periodic with n over 2, with that factor. Okay. So this is exactly the same as this. This is exactly the same as this. That's great. So we're going to simplify it more by using this periodicity, and that will allow us to further simplify it. So if you think about the first n over 2 points, okay, the first n over 2 points you're going to calculate, gk and w of n to the power of k. If you just look at the first part of the sequence, okay, k less than n over 2 and greater than 0. Okay? Great. What about the next part? How this helps us to compute the next part? Okay? We computed for all these k's already. We're going to compute for the next k's. Let's say our n was 8. We computed for 0 to 3. Now 4 to 8. How we can exploit this? Okay. So first of all, we need to know what this factor is for the second part. Right? And if you think about what this factor is, it's n over 2 less than k less than n of that, so it's really k plus n over 2. Okay, that's the second part. If you add n over 2, you get the second part. Okay. And what about x? So there's two things that we need to understand. What is this and what is this? Okay? So what are these? So what are these? If you actually write it down, you'll see that they're in fact negative of each other. When you add this plus n over 2, you get the conjugate, right? You get the conjugate, so you get a negative, like a negative power of this, right? And this one is the same. Okay. So all you really need to do now, if you think about it, it's kind of like a pi factor, right? Basically it's a pi factor. So all really you need to do now is if you want to calculate this for n equal 2, you get the original one, and then you just subtract this factor. Okay? So for the first part, you add them. For the second part, because these omegas are just negative of each other, these W's are negative of each other, you just need to subtract them. Okay? So we previously also calculated this is for the first part. Now, we already calculated that. So we don't need to recalculate those values again. We just need to add them in the beginning and then subtract them at the end. So that gives us some saving in computation. So if you write it down, it looks like this. Okay? For the first part, you multiply by these W's and then add things together. And for the second part, you take the same result and just subtract them. Now what's exciting about this, there's an operation here that's happening, you'll see over and over again. It's what's called this butterfly operation, effectively. So if you look at what's G0 and H0, how they lead X0, is they just add with this twiddle factor, which is a constant. And then to get X4, you need to then subtract them. So that operation here is called a butterfly operation, where you compute something and then you put you minus here and then a plus here and then you multiply these together. Okay, to get a result. This is a really important operation in DSP. It happens over and over and over and over again. Okay? And you'll see that's going to happen again and again. Okay, so now we look at this. It's still O of n square operations. It's more simple. Okay, I don't need to compute, that many W sub n's, right? Which is great. I finish over here, and then I just multiply. Okay? So now, we did this. Now what we could do is try to address each one of these and see whether we can decompose that. And we know we can, because if we had some, high power 2, then we can decompose that as well into even and odds. So let's do this. So if we started with an n equals 8, now we're going to do an n equals 4 DFT. Okay, so we're going to divide it again, split the even and odds in the evens. Do you see what I'm saying? Among all the evens, now we're going to split the even and odds of these. Okay? So 0 and 4, and then 2 and 6. Perform a n over 4 point DFT of them, and then do, again, this butterfly operations to get the results. Okay? Now, if you look, the inputs have been reordered. Before we reordered to even and odds, now they're reordered again. Okay? Do you want to go forward? You continue on. Like we can. This is n over 4. Let's do n over another step, right? What is the n over 4? The n over 4 for a 8-point DFT is just a 2-point DFT. Okay? What's a 2-point DFT? Look at this. What's cool about a 2-point DFT is that a 2-point DFT, you've got two numbers, and you want to get the frequency domain of two numbers. How do you get frequencies out of them? It's two operations that you can do. You add them together, you get the DC. You subtract them, you get the AC. Right? Like the Nyquist frequency. That's it. So add, subtract. Recognize that operation? It's exactly like the butterfly operation. So it comes down to be taking this one, add them, that will give you this, and then subtract them, it will give you this. Okay? Putting it all together into a tree, there you go. You've broken, and you got to the end where you just take these, add, subtract. You get some result. You take these, add, subtract, you get some result. Multiplying by a total factor. You take these, add, subtract, get a result. You take these, add, subtract, multiply by total factor. Okay? Then you end here, and then here's what you do. You kind of add, subtract, right? and get a result. You add, subtract, get a result. Add, subtract, get a result. And then for these guys, you add, subtract, multiply by total factor. Add, subtract, total factor. Then you end up here. And then again, you add, subtract, and so on and so forth. Okay? But now, if you actually count the number of operation, every time you break your DFT into smaller and smaller pieces, and at the end, it's just going to be an order of n time operation. Right? So each step is an order of n time operations. How many operations you do? If you break it every time into a factor of 2, a log number of operations. Hence the n log n. Okay? So I'm going to finish right now. We're going to continue next time on the DFT, on the FFT. Okay? And I'm going to talk about the lab. So I'm going to show you we'll walk through it and explain. It's a really cool lab. Basically, you build a sonar out of your laptops. Okay? You know, that kind of thing. You'll be able to move your hands and see them reflecting sound and see how far they are and things like that. Okay? In real time. If it works. Okay? All right. See you on Friday. And I hope to see most of you tonight.